Tonight, we're going to explore something that seems ordinary at first, but is actually one of the most puzzling phenomena in the skies, a strange light in the heavens. You've probably noticed unusual lights, shapes, or movements in the sky before. Scientists and sky watchers talk about these things often when studying the atmosphere and space. But here's what most people don't realize. When you try to understand what these mysterious events really are, when you begin to consider all the explanations, from natural to unknown, it changes how you see the world above us. This is not just a flicker or a flash. It's a phenomenon so unusual that it challenges our understanding of what's happening above our heads. And by the end of this journey, you're going to understand exactly why people keep watching the skies and why some questions remain unanswered. Before we go any further, if you enjoy slow, deep explorations like this, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Above the clouds, beyond the reach of ordinary eyes, the night sky sometimes hosts a fleeting and remarkable display. It is a phenomenon so delicate and so brief that it can vanish almost as soon as it appears. These flashes of red light, known as red sprites, hover silently above thunderstorms, far above the lightning that strikes the ground. They are not the lightning most people see, the bright forked streaks that crash across the sky, but a different kind of electrical spectacle. Their presence has only been confirmed through careful observation and modern technology, although scattered reports hinted at their existence for decades before science could verify them. Red sprites are a type of transient luminous event, an upper atmosphere phenomenon linked to powerful electrical storms. Unlike typical lightning, they appear in the mesosphere, at altitudes ranging roughly from 50 to 90 kilometers above the Earth. They are short-lived, lasting only a few milliseconds. But in that time, they trace shapes that can resemble dancing columns, clusters of tendrils, or even carrot-like formations. The red color dominates, produced by the excitation of nitrogen molecules in the thin air at those high altitudes. When these molecules regain their normal state, they emit light that is visible as a reddish glow. Blue or violet hues can sometimes appear at lower tips of the sprite, hinting at complex interactions with atmospheric gases. Before the advent of high-speed photography and sensitive low-light cameras, red sprites remained largely invisible to casual observers. Storm watchers occasionally reported unusual flashes, but these were often dismissed as anomalies or mistaken for distant lightning. It was only when cameras could record frames at thousands of images per second that the true nature of red sprites became undeniable. In the 1980s, scientists working from mountaintops and aircraft above storm clouds captured the first reliable evidence of these events. The images revealed forms stretching upward, delicate and branching, reaching into the high mesosphere above thunderstorms. What had been almost invisible to human eyes was suddenly a subject of study, a new piece in the puzzle of atmospheric electricity. Researchers realized that red sprites were tied closely to the behavior of positive lightning strikes, the unusually strong discharges that carry high voltage from clouds to the ground. These strikes produce electrical fields intense enough to disturb the rarefied air above storms, triggering the luminous sprites. The energy involved is substantial, yet subtle compared to the storms themselves. Each event unfolds quickly, but when viewed in slow motion, it reveals complex patterns of ionization and electric discharge that connect the lower atmosphere with the upper reaches above. The sprites do not follow the paths of ordinary lightning. Instead, they appear as sudden bursts that climb, branch, and fade in the upper layers of the atmosphere. Their shapes and motions seem to respond to the structure of the thunderstorm below, to the placement of the charge pockets, and to the prevailing conditions in the mesosphere. Observing red sprites requires patience, careful timing, and the right vantage point. The best conditions occur when a powerful thunderstorm rages on a distant horizon, and the sky above it is dark and clear. From that distance, the bright lower lightning does not overwhelm the faint flashes of the sprite. Observers using sensitive cameras or video equipment can capture hundreds of frames that show the development of a single event. Each sprite begins as a faint glow, rising upward, quickly branching into filaments or columns, and then fading almost entirely. Some events last only a few milliseconds, while others persist for tens of milliseconds. In that short interval, the sprite can extend tens of kilometers in vertical height, dwarfing the storm that spawns it below. These fleeting forms challenge human perception, requiring both keen attention and technological assistance to study in detail. Researchers have learned to synchronize cameras with storm monitoring systems so that sprite events can be captured precisely at the moment a positive lightning strike occurs. These measurements confirm that the intensity, polarity, and location of the lightning influence the size, shape, and brightness of the sprite. While casual observers rarely see these phenomena, scientific observation has revealed them to be both regular and repeatable, part of a broader system of atmospheric electricity that links the weather on the ground with layers high above the planet. The study of red sprites also illustrates how natural phenomena can exist for decades or even centuries before humans notice or understand them. Early reports of strange red flashes above storms, often anecdotal, could not be confirmed. But with improved instrumentation, the phenomenon was not only captured but analyzed. Spectroscopic studies have shown that the red color comes primarily from excited nitrogen molecules emitting light at characteristic wavelengths. The blue and violet tips observed in some sprites are related to ionized nitrogen and interactions with the lower layers of the mesosphere. These subtle differences in color provide clues about the temperature, pressure, and composition of the air at those heights. Scientists can use sprite observations to infer conditions far above the clouds in a region that is otherwise difficult to study. The occurrence of sprites also varies with storm type, geographic location, and season, suggesting that they are connected to larger patterns of atmospheric electricity. They are most frequently observed over continents where intense thunderstorms generate strong positive lightning, although they can appear over oceans as well. Tracking these events globally helps researchers understand how energy flows from the lower atmosphere into the mesosphere and how electrical systems in the atmosphere interact with one another across vast distances. Despite their rarity in human observation, red sprites are not extraordinary in terms of occurrence. Modern studies show that thousands of sprites may occur globally each day, even if most go unnoticed. Their brief, delicate forms are a reminder of the dynamic and layered nature of the atmosphere. Above the visible storm clouds, where the sky fades into darkness, the mesosphere can host these subtle bursts of energy, quietly tracing patterns that follow the invisible currents of the Earth's electrical system. Observers who capture these events gain more than just photographs. They gain insight into the processes that connect the storm below to the upper atmosphere. In turn, this understanding contributes to broader studies in meteorology, climate science, and space weather. Sprites are one piece of a vast puzzle, illustrating that the sky is alive with electrical activity in ways that are largely hidden from direct human perception. Each observation confirms that thunderstorms are not confined to the clouds themselves, but extend their influence far above. generating fleeting, luminous structures that appear almost magical, but are entirely natural and measurable. Red sprites also challenge the way people perceive lightning and storm phenomena. Most consider lightning to be a surface-level event, dramatic and visible as it strikes the ground or clouds. Yet, sprites demonstrate that storms are layered, with energy moving both downward and upward. This upward discharge is subtle, fast, and often invisible without technology. In studying sprites, scientists have identified the conditions that favor their formation: strong positive cloud-to-ground lightning, high altitude charge buildup, and low atmospheric density. The presence or absence of these conditions can change whether a sprite appears or remains unseen. The shapes of sprites, including columns, tendrils, and branching carrot-like forms, are not random. They reflect the structure of the electrical field in the mesosphere, the distribution of charges in the storm below, and the pathways along which ionization can propagate. Observing these forms in detail allows researchers to test theories about electrical discharge in thin air, the propagation of ionization fronts, and the interaction between charged particles at high altitude. By combining visual observation, spectroscopy, and timing with the lightning below, researchers have developed a more complete understanding of sprite events. The phenomenon connects ground-level weather with conditions tens of kilometers above, demonstrating that the atmosphere is a continuous, interactive system rather than a set of disconnected layers. Each sprite captured in an image or video tells a story about the storm below, the electrical forces at play, and the behavior of gases in the mesosphere. Observations also suggest that sprites may influence the upper atmosphere in subtle ways, affecting ionization levels, transient currents, and possibly even atmospheric chemistry. While the effects are small compared to the scale of the atmosphere, they are measurable and contribute to a growing understanding of the Earth's electrical environment. Red sprites, then, are both a visual phenomenon and a window into the physics of the sky above, an example of how delicate and transient events can reveal deep truths about the natural world. The excitement surrounding red sprites has grown alongside technological advances in observation, from the early grainy images to high-resolution, high-speed video. Each generation of research tools has revealed more detail about the structure, duration, and occurrence of these events. Scientists now routinely capture sprites from aircraft, satellites, and ground-based cameras, allowing for comparative studies across storms and continents. These observations reinforce the connection between positive lightning and sprite formation, clarify the role of atmospheric composition, and provide data for testing theoretical models of electrical discharge at high altitude. While still mysterious in some ways, red sprites have shifted from anecdotal curiosity to a well-documented phenomenon, demonstrating the power of modern science to reveal events that were previously invisible. They show that even in the quiet of a distant storm, in the upper reaches of the sky, complex electrical activity continues in forms both beautiful and scientifically significant. The story of red sprites begins with these first observations and the slow accumulation of knowledge that allows humans to see beyond the ordinary, to detect the hidden flashes that trace the invisible forces above the clouds. Red sprites do not appear in isolation. They are part of a larger system, connected intimately to the storms below them. Thunderstorms are more than clouds filled with rain and wind. They are massive engines of electricity. Within their towering walls, air is moved rapidly upward and downward, carrying moisture, ice, and charged particles. Collisions between ice crystals and water droplets create pockets of positive and negative charges, The lower part of the storm tends to hold negative charge, while the upper regions accumulate positive charge. When the difference in charge becomes large enough, a lightning discharge occurs. This movement of electricity is familiar as the forked, bright streaks that strike the ground or connect cloud to cloud. Yet, a less obvious effect takes place above the storm, in the upper atmosphere where the air is thinner, colder, and less dense. The electric fields generated by powerful lightning can extend tens of kilometers upward, reaching the mesosphere. It is in this rarefied region that red sprites are born. Positive lightning strikes, in particular, play a central role in the creation of red sprites. Unlike more common negative lightning, which moves from the cloud toward the ground, positive strikes carry a large amount of charge from the upper part of the storm down to the surface. This discharge is more energetic and less frequent than negative lightning. When such a strike occurs, it leaves behind an intense, quasi-electrostatic field above the storm. This field can disturb the charged particles in the mesosphere, triggering a sudden breakdown of the air. In this breakdown, electrons are accelerated along preferred paths, ionizing the thin air as they move. The result is a luminous burst of red light, a sprite. The color emerges from the excitation of nitrogen molecules, which release energy as visible light when they return to their normal state. While the ground sees the brilliant flash of lightning, the upper atmosphere responds with a subtler, more delicate light show that often goes unnoticed by observers at lower altitudes. The structure of a red sprite is influenced by the shape and intensity of the electrical field above the storm. When a positive lightning strike occurs, the field is strongest directly above the main charge region. Ionization begins there, forming the first glow that will develop into tendrils, columns, or carrot-like shapes. The paths of these forms are not random. They follow the lines of electrical potential, branching outward as the electrons accelerate along areas of least resistance. The speed of the process is remarkable. A single Sprite event can unfold in a few milliseconds, rising tens of kilometers into the mesosphere. The shapes can vary widely, influenced by the size of the underlying storm, the intensity of the lightning, and the distribution of charges in the upper atmosphere. In some cases, clusters of sprites appear above a single storm, each one a brief luminous echo of the electrical energy released below. Scientists studying these events have noted the importance of storm height and intensity. Taller storms, those with strong updrafts that carry moisture and ice high into the sky, are more likely to generate positive lightning. These storms can reach altitudes of 10 to 20 kilometers, with charges building in multiple layers. The higher the storm extends, the closer it comes to the mesosphere where red sprites form. Storms in continental interiors, particularly during summer months, are often the most productive. The combination of dry air near the surface and moisture-laden updrafts creates conditions for intense charge separation. When conditions are right, the positive lightning that produces sprites is more likely to occur. Observers and instruments positioned at a safe distance, often tens of kilometers away, can capture these events without interference from the brighter flashes of lower lightning. High-altitude photography and video have allowed researchers to see how each sprite begins, grows, and fades, revealing the intimate link between the thunderstorm and the upper atmosphere event. The troposphere, where weather occurs, is electrically active. Each storm acts as a generator, moving charge and creating potential differences. These differences extend beyond the visible clouds, influencing regions above. The stratosphere and mesosphere, while less dense and colder, are sensitive to strong electric fields. In these layers, free electrons can accelerate quickly, ionizing molecules along their paths. The breakdown of air occurs more easily at these high altitudes because the pressure is lower and collisions between particles are less frequent. This is why sprites can extend over tens of kilometers with relatively modest energy compared to the lightning that strikes the ground. The process is brief, but the interaction is significant, providing a direct link between weather phenomena we see and electrical activity in the upper atmosphere. Sprites, therefore, are not an isolated curiosity. They are a consequence of a chain of events initiated in the storm below. Historical observations of unusual flashes above storms were noted as early as the 19th and 20th centuries, but understanding their connection to thunderstorms required both careful timing and technological innovation. Researchers hypothesized that electrical activity in the troposphere could extend upward, affecting the rarefied air of the mesosphere and stratosphere. Experiments in the 1970s and 1980s began to confirm this idea. High-speed cameras, synchronized with lightning detection systems, captured the first clear evidence. The timing was critical. Sprites appear almost immediately after a strong positive lightning strike, and their duration is so short that standard cameras could not detect them. Spectroscopic analysis showed that the red light was consistent with excited nitrogen molecules. Observers working from mountain peaks or high-altitude aircraft could finally see that these bursts were not optical illusions, but genuine electrical events. The connection to thunderstorms was undeniable. Each sprite followed the occurrence of a storm, appeared above it, and mirrored the patterns of electrical charge that the storm had produced. The ionosphere also plays a subtle but important role in upper atmosphere interactions. Located hundreds of kilometers above the Earth, it contains charged particles that can influence electrical fields below. While red sprites form well beneath the main ionospheric layers, the boundary between the mesosphere and ionosphere is affected by charged particle movement. Electric fields from storms propagate upward, interacting with these layers and creating conditions suitable for sprites to appear. Studies of these interactions help scientists understand not only sprites, but also other upper atmosphere phenomena, including jets, elves, and blue starters. Each of these events is connected to thunderstorms in some way, but sprites remain distinct in their red color, shape, and brief vertical reach. Observing how the electrical energy travels from the storm to the sprite allows researchers to map the flow of electricity across multiple layers of the atmosphere, bridging the gap between meteorology and upper atmosphere physics. Experiments on the ground and in laboratories have reproduced aspects of sprite formation, providing insight into the electrical mechanisms involved. By generating high-voltage discharges in low-pressure chambers, scientists can study how electrons accelerate and how nitrogen molecules emit light when excited. These studies show that the branching forms of sprites correspond to regions where the electric field is strongest. The process begins as a faint glow, often unseen by the naked eye, which grows and splits into filaments. Each filament represents a path along which electrons ionize air molecules. The branching continues until the field dissipates or the sprite fades. This controlled reproduction in the lab helps explain why sprites are so sensitive to the underlying storm. Variations in lightning, intensity, cloud height, and charge distribution can produce dramatically different sprite shapes, even from storms of similar size. The laboratory work, combined with high-speed observational data, provides a comprehensive understanding of the interaction between thunderstorms and upper atmosphere electrical events. Sprites also reveal how energy from the lower atmosphere is transferred upward in ways previously unappreciated. A storm's charge distribution creates a vertical electric field that reaches far above the clouds into a region where the air is less dense and electrons move more freely. Positive lightning releases energy that disturbs this region, triggering ionization that becomes visible as a red sprite. The energy involved is modest relative to the overall storm, but concentrated enough to produce a visible effect. Researchers can measure the brightness, duration, and vertical extent of sprites to calculate the energy transferred. These measurements show a clear relationship between the strength of the lightning and the size of the sprite. In effect, red sprites act as markers, tracing the invisible pathways of electrical energy from the storm to the upper atmosphere. Each observation adds to our understanding of how storms influence the sky above, revealing the complex and interconnected layers of Earth's atmosphere. Above all, red sprites demonstrate the continuity of atmospheric processes. The troposphere, stratosphere, and mesosphere are not separate systems, but layers that interact through electrical forces. A storm's energy does not end at cloud tops, but can reach tens of kilometers higher, manifesting in transient luminous events. Positive lightning provides the trigger, while the mesosphere offers the stage. Sprites are the result, appearing suddenly and briefly, then fading as the energy dissipates. Observing them allows scientists to witness the invisible consequences of storm activity and to understand how energy moves from the weather we see to the layers above. They are delicate, ephemeral, and yet profoundly informative, providing a direct link between ground-level thunderstorms and the electrical dynamics of the upper atmosphere. In this way, the study of red sprites deepens our understanding of the sky, revealing that the night is alive with energy even far above the clouds, where ordinary eyes seldom reach. Red sprites are remarkable because they reveal the physics of electricity in an environment far different from the surface. Unlike ordinary lightning that moves through the dense air of the lower atmosphere, sprites form in the mesosphere, where the air is thin and collisions between molecules are less frequent. This low density allows electrons to accelerate more freely, creating long, branching streams of ionization that emit light. The initial trigger for a sprite is almost always a strong positive lightning strike. When a cloud discharges positively to the ground, it leaves a strong electric field in the space above the storm. This field is known as a quasi-electrostatic field because it changes more slowly than the lightning itself, but it is intense enough to accelerate electrons along paths of least resistance. As electrons move, they collide with nitrogen molecules, exciting them. When the molecules return to their normal state, they release photons, producing the red glow characteristic of sprites. The light appears quickly, often within a few milliseconds after the lightning strike, and can extend vertically for tens of kilometers. The process begins with the formation of streamers, narrow channels of ionized air that grow upward from regions of strong electric potential. Each streamer propagates as electrons move forward, colliding with air molecules and creating more free electrons. Branching occurs naturally where the electrical field is uneven, creating the delicate, tree-like structures seen in photographs. Streamers can merge, split, or form clusters, giving rise to the varied shapes of sprites. Sometimes, a single sprite consists of one central column with multiple tendrils, while other times a wide cluster of short carrot-shaped streamers appears simultaneously. The exact shape depends on the storm below, the distribution of charges, and the local density of the atmosphere. Streamer growth is extremely fast, measured in kilometers per millisecond, yet the visible phenomenon remains brief, with most sprites lasting only 5 to 20 milliseconds. Despite their short duration, sprites are tall, extending as high as 90 kilometers above the Earth in some cases. Their vertical reach dwarfs the storms that trigger them, illustrating how energy moves upward from the troposphere into the mesosphere. The atmosphere itself affects how sprites appear. The mesosphere contains mostly nitrogen and oxygen, with traces of other gases. Nitrogen is the primary source of the red light, because when electrons excite nitrogen molecules, they emit photons in the red spectrum. At lower altitudes, where pressure is higher, collisions between molecules occur more frequently, changing the way light is emitted. Blue and violet hues can appear at the lower tips of sprites, where the density of air is slightly greater and ionization occurs differently. The precise combination of nitrogen excitation and electron acceleration determines the color, brightness, and shape of the sprite. Researchers have studied this relationship extensively, using spectroscopy to identify the wavelengths of light emitted and to estimate the energy involved. The light of a sprite is faint compared to the lightning of the storm below, but it is enough to reveal the movement of electrons and the structure of the electric field in the mesosphere. Sprites are distinct from other upper atmosphere lightning phenomena. Blue jets, for instance, are narrow streams of light that emerge from the tops of clouds and move upward into the stratosphere at speeds of roughly 100 kilometers per second. They are generally slower than elves, which are rapidly expanding, disc-shaped flashes caused by electromagnetic pulses from lightning. Elves appear almost instantaneously, spreading horizontally over hundreds of kilometers, and are blue or purple in color. Sprites, in contrast, are red, vertical, and more structured. They do not move upward as a single flash, but rather develop through the growth of multiple streamers. The distinction between these events is important for researchers studying upper atmosphere electricity, because each represents a different mechanism and energy scale. Sprites are triggered primarily by strong positive lightning, while jets and elves may be initiated by different types of discharges or electromagnetic effects. Observing and classifying these phenomena allows scientists to understand the diversity of electrical events in the upper atmosphere and their relationship to storms below. The energy involved in sprite formation is significant but modest compared to the storm itself. Positive lightning transfers large amounts of charge to the ground, generating a quasi-electrostatic field above the cloud. The sprite uses a small fraction of this energy to accelerate electrons and produce light. Measurements suggest that a single sprite event involves tens to hundreds of kilojoules, a tiny portion of the gigajoules released in the lightning strike below. The efficiency of light production is low, as most energy is spent moving electrons and creating ionized paths rather than radiating visible light. Despite this, the resulting structures are large, tall, and visually distinct. The height and reach of sprites depend on the local atmospheric density. At higher altitudes, where air pressure is low, streamers can extend further before colliding with molecules, producing the long filamented shapes seen in many photographs. At lower heights, the streamers are shorter and more compact, sometimes appearing as clustered tendrils or diffuse red patches. Temporal characteristics of sprites are also well defined. They begin almost immediately after the triggering lightning strike, with a delay typically of 1 to 5 milliseconds. The development of the streamers occurs rapidly, rising tens of kilometers in a fraction of a second. Most sprites fade completely within tens of milliseconds, although some complex events may produce multiple bursts over a longer period. The brief duration, combined with the faint intensity relative to ordinary lightning, explains why they remained unnoticed until the late 20th century. High-speed cameras and sensitive photometers are necessary to capture the sequence of growth, branching, and decay. By analyzing these observations frame by frame, researchers can reconstruct the dynamics of the sprite, measure its vertical and horizontal extent, and study the behavior of electrons in the thin air of the mesosphere. The physical environment of the mesosphere contributes to sprite behavior. Temperatures are extremely low, often below -80 degrees Celsius, and the air density is only a few % of that at sea level. The lower pressure reduces collisions, allowing electrons to move longer distances before interacting with molecules. This results in longer streamers and taller sprites. The relative absence of clouds and water vapor at these altitudes also reduces scattering of light, making the sprite more defined. Variations in air density, temperature, and background ionization influence whether a sprite develops a single column, multiple tendrils, or a wide cluster. Scientists use models to simulate these conditions, reproducing streamer formation and propagation in the lab under low-pressure conditions. These models help explain why sprites are sensitive to both the intensity of the lightning below and the subtle properties of the upper atmosphere. Sprites are not only visual phenomena, but also electrical markers. Each event traces the movement of charge from the storm to the upper atmosphere. By studying sprites, researchers can estimate the strength and distribution of electric fields above thunderstorms. Observations show that sprite clusters often align with regions of strong positive charge within the storm, confirming the link between the lower atmosphere and high-altitude events. Streamer density, branching patterns, and vertical reach provide insight into the behavior of electrons and the electrical conductivity of the mesosphere. Sprites thus serve as a natural laboratory, allowing scientists to observe how electrical energy propagates in thin air, interacts with molecular gases, and generates transient luminous events. Laboratory studies support these observations. High-voltage experiments in low-pressure chambers simulate the conditions of the mesosphere. Researchers accelerate electrons through nitrogen-rich air, observing streamer formation, branching, and light emission. These experiments reproduce the red glow of sprites, confirming that nitrogen excitation is the primary source of color. Variations in pressure, voltage, and gas composition create different streamer behaviors, demonstrating why sprites can appear as columns, tendrils, or clustered shapes. The laboratory results align closely with high-speed observations, validating the physical models. This combination of field observation and controlled experimentation provides a complete picture of the electrical and optical processes behind red sprites. The study of sprite physics has revealed their connection to larger atmospheric systems. By tracing how positive lightning initiates upward discharge, scientists understand how storms influence layers far above cloud tops. Sprites illustrate that electrical energy does not remain confined to the troposphere. It reaches into the mesosphere, producing visible signals and transient currents that are measurable with modern instruments. Each event contributes to the growing knowledge of how Earth's atmosphere conducts electricity, how energy moves through thin air, and how different layers interact. The red glow that flickers above a storm is not simply a curiosity. It is a window into the dynamics of high-altitude electricity, shaped by the forces of storms below and the delicate structure of the air above. Through careful observation and analysis, the physics of red sprites continues to reveal the subtle complexity of our planet's electrical environment. Red sprites are delicate and fleeting, and for many years they eluded human observation. Even though thunderstorms and lightning have been watched for centuries, these upper atmosphere phenomena were almost entirely invisible to casual observers. Their brevity, faint intensity, and high altitude make them difficult to detect with the naked eye. A sprite may last only a few milliseconds, rising tens of kilometers into the mesosphere, and its red glow is faint compared to the bright flashes of lightning in the storm below. From the ground, these bursts can blend into the background darkness or be completely obscured by clouds or precipitation. Early anecdotal reports of red flashes above storms were often dismissed, recorded as optical illusions, or mistaken for distant lightning. Without technology capable of capturing events on such short timescales and low brightness levels, red sprites remained largely hypothetical, known only through speculation and fragmentary eyewitness accounts. The human eye has limits that contribute to the difficulty of observing sprites. Eyes adapted to low light are more sensitive to blue and green light than to red. The red color of sprites is therefore naturally hard to detect. Additionally, the short duration of a sprite event means that the eye cannot process the full shape before it fades. Bright lightning below storms further diminishes visibility. When the lower lightning flashes, it floods the retina with light, temporarily reducing sensitivity and making any upper atmosphere flashes harder to see. Observers on the ground needed not only dark skies and clear lines of sight, but also careful timing to catch the sprite in the instant it occurred. Atmospheric conditions such as haze, fog, or even distant clouds could scatter light and hide the event. The combination of faint intensity, brief duration, and visual interference from storm lightning made it no surprise that sprites were unknown until the late 20th century. Storm positioning is another key factor in the visibility of sprites. Because sprites occur directly above thunderstorms, the observer must have a vantage point that allows an unobstructed view of the storm. Hills, mountains, or distant plains can offer better angles, especially when the storm is far enough away that the lower lightning does not overwhelm the upper atmosphere light. Observers must position themselves at the right distance. Too close, and the storm's bright lightning dominates the scene. Too far, and the sprite's faint red glow is lost against the dark horizon. Season, geography, and storm size all affect the likelihood of seeing a sprite. Tall, intense storms with strong positive lightning are most likely to produce sprites. Observing at night increases visibility, but requires patience and careful preparation. Photographers and scientists have had to wait for storms to develop in the right location, using maps, satellite images, and weather reports to plan their observation campaigns. This combination of natural conditions and technical preparation limited early observations to rare and fortunate circumstances. Early cameras were inadequate for capturing sprite events. Standard film cameras or early video equipment could not operate at the high frame rates needed to record events lasting only milliseconds. Moreover, conventional cameras lacked the sensitivity to capture faint red light in dark skies. Even when the equipment was pointed at a storm, most sprites would remain invisible on the film. Observers had to innovate to detect and record these events reliably. High-speed photography became essential, with cameras capable of thousands of frames per second. This technology allowed researchers to slow down the rapid development of sprites and study their structure, branching, and duration. Low-light cameras, developed for astronomy and military purposes, provided the sensitivity needed to capture the red glow against a dark sky. In some cases, scientists mounted these cameras on aircraft or balloons, placing them above the cloud layer to reduce interference from the storm and improve clarity. Satellite observation also revolutionized Sprite research. From space, satellites can monitor large areas of the atmosphere simultaneously, tracking storm systems and their electrical activity. Specialized instruments measure transient luminous events, detecting flashes of light in the mesosphere, even when ground-based observers cannot see them. Satellite data confirm that Sprite events occur globally, above both continental and oceanic storms. This global perspective allowed scientists to understand the frequency, distribution, and conditions associated with Sprite formation. Combining satellite observations with ground-based photography created a more complete picture of these elusive phenomena. Observers could now correlate Sprite occurrence with storm intensity, lightning type, and geographic factors, revealing patterns that had previously been hidden. Even with advanced cameras and satellites, capturing sprites requires careful timing and coordination. Positive lightning, the primary trigger for sprite formation, is unpredictable. Researchers often monitor storms for hours, waiting for the right strike to produce a visible event. Observers use lightning detection networks to anticipate which storms are likely to produce positive strikes. When the lightning occurs, high-speed cameras record hundreds or thousands of frames in milliseconds. The images reveal the sprite growing, branching, and fading in the upper atmosphere. Spectroscopic instruments analyze the light to determine its composition and energy. Each successful observation provides new insight into the conditions necessary for sprite formation and the structure of the electrical field above storms. Without this coordination and technology, sprites would remain invisible to human perception, their existence suspected but unproven. Atmospheric clarity is critical for observing sprites. Dust, haze, or moisture in the lower atmosphere scatters light and diminishes visibility. Observers often seek locations with dry air, clear skies, and minimal light pollution. Mountain peaks, high plateaus, and open plains provide ideal vantage points. Observing over oceans can be effective because storms are isolated and the air is relatively clear, though logistics are more difficult. The combination of clear air, dark skies, and distant storms allows faint red flashes to be recorded without interference. Even small changes in weather can affect visibility, demonstrating how delicate and sensitive sprite observation is. Researchers must plan carefully and adjust quickly to changing conditions, highlighting the challenges inherent in studying these transient events. Advances in digital imaging have further improved sprite observation. Modern cameras offer high sensitivity, high frame rates, and precise timing with GPS or lightning detection networks. Image processing software can enhance faint features, allowing the branching tendrils and columnar structures to be analyzed in detail. Video sequences show the development of a sprite from initial glow to full structure to fade, providing a dynamic view of the electrical process. These images allow scientists to measure altitude, duration, energy, and morphology. With improved resolution and frame rates, subtle variations in streamer formation can be studied, revealing how electrical fields interact with the thin air of the mesosphere. This detailed observation was impossible before the development of such technology, explaining why sprites remained hidden for so long, despite the centuries of storm watching that preceded modern science. Despite these advances, sprites are still elusive for casual observers. Their brevity, faint color, and position above storms make them easy to miss. Only with specialized equipment and careful planning can they be reliably recorded. The history of sprite observation demonstrates how technology shapes our understanding of natural phenomena. Where human eyes fail, cameras succeed. Where anecdotal reports exist, instruments provide confirmation. High speed, low light, and satellite imaging together have revealed the full range of sprite behavior, including vertical height, branching patterns, and correlation with storm electricity. This progress shows that observing the upper atmosphere requires both patience and ingenuity, and that sprites are a subtle but integral part of the electrical processes in the sky. In summary, the difficulty of observing red sprites results from their faint red glow, extreme brevity, high altitude, and interference from the storms below. Human eyes alone cannot reliably detect them, and early cameras were too slow or insensitive. Storm positioning, night conditions, and atmospheric clarity all influence visibility. Advances in high-speed photography, sensitive video equipment, and satellite instruments have made sprites accessible to scientific study. Through careful timing and coordination, researchers now capture the precise development of these fleeting events, revealing their structure, duration, and connection to positive lightning. Observing sprites remains a challenge, but each successful recording adds to the understanding of how storms extend their influence into the upper atmosphere, creating luminous phenomena that were once invisible to human perception. The study of red sprites moved from speculation to fact through a series of careful observations and coordinated campaigns. Before the late 20th century, the phenomenon was mostly anecdotal. Pilots, storm chasers, and observers occasionally reported brief red flashes above thunderstorms, but these reports could not be verified scientifically. The transition from uncertain reports to reliable evidence began with ground-based observation campaigns, where researchers positioned cameras at high elevations to monitor thunderstorms. Scientists realized that capturing these brief, faint events required both patience and precise technology. Observatories located on mountain peaks, far from city lights, became primary sites for systematic study. Here, teams of researchers could aim sensitive cameras toward distant storms and wait for the appearance of red sprites. The first successful images revealed unexpected details: tall columns of red light, branching tendrils, and complex shapes extending into the mesosphere above the storm. NASA played a significant role in bringing sprite research into mainstream science. In the early 1980s, the agency supported airborne observation missions that carried high-speed cameras above thunderstorms. From these vantage points, cameras could look down through clear layers above cloud tops, avoiding the visual interference of the storm below. Flights over the central United States, a region prone to strong summer thunderstorms, allowed repeated observations. Each mission provided data on sprite occurrence, duration, and structure. These missions confirmed what ground-based observers had begun to suspect. Red sprites were not rare anomalies, but a common, natural consequence of strong positive lightning. NASA's work also provided precise timing data, showing that sprites typically appear a few milliseconds after the triggering lightning strike. This timing confirmed theoretical predictions about quasi-electrostatic fields propagating upward into the mesosphere and creating conditions favorable for ionization and streamer formation. Early researchers such as John Winkler, Walter Lyons, and others pioneered these investigations. Winkler, an atmospheric physicist, contributed to the first systematic airborne observations, using sensitive cameras and photometers to capture faint red flashes. Lyons, based in New Mexico, coordinated ground-based campaigns that combined cameras with lightning detection networks. These researchers faced significant technical challenges, including the need to synchronize high-speed photography with unpredictable lightning events. Lightning occurs without warning, so instruments had to be ready continuously, capturing hundreds of frames per second. When successful, these campaigns produced the first consistent photographic evidence of sprites, showing their vertical columns and branching structures with clarity. Such documentation transformed sprites from anecdotal curiosities into scientifically validated phenomena. The first high-speed video sequences revealed the dynamics of sprite formation in remarkable detail. Observers could see a faint glow emerging above a storm, quickly developing into vertical columns that branched and spread. Each streamer extended tens of kilometers upward, forming carrot-like shapes or clusters of filaments. The timing of the event was consistent with theoretical models. The sprite appeared shortly after a strong positive lightning discharge, grew rapidly, and faded within tens of milliseconds. Spectroscopic measurements taken alongside these observations confirmed the source of the red light as nitrogen excitation in the thin air of the mesosphere. Some video sequences also captured subtle blue or violet hues at the lower tips of sprites, illustrating the effects of air density and molecular interactions. These early visual records provided not only confirmation of theoretical predictions, but also data to refine models of sprite formation and development. Ground-based campaigns revealed patterns in sprite occurrence. Observers noted that sprites were more common over continental interiors, where powerful thunderstorms with strong positive lightning were frequent. They also appeared more often during the late spring and summer months, when storm conditions were most intense. By carefully documenting the conditions of each observation, researchers could correlate sprite formation with lightning type, storm height, and geographic location. This correlation reinforced the understanding that sprites were directly triggered by upper atmosphere electrical conditions initiated by specific lightning strikes. Each observation built upon the last, forming a growing database of reliable evidence and establishing sprites as a repeatable and measurable phenomenon rather than a one-off curiosity. Expeditions also tested the theoretical understanding of sprite formation. By using synchronized instruments, scientists could measure the electric fields above storms, the timing of lightning strikes, and the corresponding sprite events. These measurements confirmed that the quasi-electrostatic field above a strong positive lightning discharge could reach sufficient strength to ionize the mesosphere. The observations also showed that streamer formation began at altitudes corresponding to the density of the upper atmosphere, consistent with predictions about electrical breakdown in thin air. The combination of theory, ground-based observation, and airborne photography provided a complete picture. Sprites were a direct, visible result of the interaction between thunderstorms and the upper atmosphere. Each new dataset strengthened confidence in the underlying physical models and allowed researchers to predict the conditions under which sprites would form. One notable breakthrough came from coordinated observations using both aircraft and ground-based cameras. By positioning cameras at different angles and altitudes, scientists could capture stereo images of the same sprite event. This technique allowed for accurate measurement of height, vertical extent, and branching patterns. Data showed that sprites often began at altitudes of around 50 kilometers, extending upward to nearly 90 kilometers. This vertical range was consistent across multiple storms and geographic locations, confirming the repeatability of the phenomenon. The stereo observations also revealed structural details invisible in single-camera images, such as subtle branching tendrils and variations in brightness along the sprite's length. Such observations helped refine models of electrical propagation and the influence of atmospheric composition on streamer behavior. In parallel, researchers developed early spectroscopic methods to analyze the light emitted by sprites. Using filters and sensitive photometers, they could isolate specific wavelengths corresponding to nitrogen excitation. These measurements confirmed that the red glow was indeed caused by molecular nitrogen returning to its ground state after being excited by accelerated electrons. In some cases, weak blue emissions at the lower tips of the Sprite indicated different ionization conditions, likely caused by higher air density or minor variations in local electrical fields. These detailed observations provided strong evidence that Sprite light emission matched theoretical predictions about electrical breakdown and molecular excitation in the mesosphere. Scientists could now connect observed visual features to underlying physical mechanisms with confidence. Early photographic campaigns also documented clusters and multiple sprites above the same storm. Observers recorded simultaneous events, showing that sprites could occur in bursts rather than as isolated flashes. This suggested that the distribution of charges within the thunderstorm created multiple regions where the quasi-electrostatic field could exceed the threshold for streamer formation. Each cluster reinforced the understanding of the relationship between storm structure and sprite formation. The photographs provided clear visual confirmation of what had previously been inferred. Sprite shapes, size, height, and temporal development could all be systematically recorded and analyzed. Over time, these images and videos built a catalogue of Sprite events that formed the foundation for modern research. By the early 1990s, red sprites were firmly established as a genuine, reproducible atmospheric phenomenon. The combination of high-speed cameras, sensitive photometric equipment, and coordinated observation campaigns allowed scientists to capture the full sequence of Sprite events. Observations confirmed the connection to positive lightning, validated the role of quasi-electrostatic fields, and demonstrated how the thin air of the mesosphere facilitated streamer formation. Laboratory experiments and spectroscopic measurements provided further support, showing that molecular nitrogen emitted light in the red spectrum when excited by high-energy electrons. Together, these breakthroughs transformed sprites from an anecdotal curiosity into a well-understood component of upper atmosphere physics. The early discoveries laid the groundwork for later studies of global occurrence, energy transfer, and the influence of sprites on mesospheric chemistry. The early breakthroughs also highlighted the collaborative nature of Sprite research. Teams of scientists across institutions shared data, synchronized observation schedules, and compared measurements to improve reliability. Pilots, storm chasers, and amateur observers contributed additional records, often providing the first sighting of a sprite in a given storm. This combination of professional and citizen science accelerated the collection of evidence and reinforced the reproducibility of findings. By connecting theory, observation, and experimentation, researchers could finally confirm the mechanisms behind red sprites and establish them as an important feature of Earth's electrical system. These discoveries marked a turning point, showing that even phenomena that are invisible or fleeting to human eyes could be studied systematically, measured accurately, and understood scientifically. Red sprites do not occur randomly across the globe. Their appearance follows patterns determined by the frequency of strong thunderstorms and the presence of positive lightning. Observations and satellite data reveal that sprites are most common over continental interiors, where warm, moist air rises rapidly to create tall, energetic storm systems. The central United States, particularly the Great Plains, is one of the most well-studied regions. During the late spring and summer months, convective storms there produce the tall cloud tops, strong updrafts, and intense charge separation that are conducive to sprite formation. Other continental regions, such as parts of South America, Africa, and Asia show similar patterns, where seasonal storms concentrate over land rather than over the ocean. These regions provide the combination of atmospheric instability, moisture, and high cloud tops necessary to produce the strong positive lightning that triggers sprites. Sprite activity is less common over open oceans, although they do occur. Oceanic storms tend to be less tall than continental storms, with lower cloud tops and weaker charge separation in the upper parts of the storm. Without tall, intense thunderstorms, the quasi-electrostatic fields needed to trigger streamers in the mesosphere are less likely to develop. However, under certain conditions, such as when large tropical cyclones produce exceptionally strong convection, sprites have been observed over water. Satellite monitoring allows researchers to capture these events in remote oceanic regions, confirming that while less frequent, sprites are a global phenomenon, not confined to any single continent. Comparing oceanic and continental events helps scientists understand how storm structure and intensity influence sprite formation. Seasonal patterns are clear in areas where sprite observation is most frequent. In the Northern Hemisphere, sprites peak during late spring through early autumn, coinciding with the season of maximum convective activity. Warm surface temperatures, high humidity, and daytime heating produce strong updrafts and towering thunderstorms, increasing the likelihood of positive lightning. Nighttime observation is essential because sprites are faint. The events often occur after sunset, when the lower lightning illuminates the clouds below, while the upper atmosphere flashes remain visible against a dark sky. Seasonal patterns also appear in the Southern Hemisphere, with peaks corresponding to summer months and active storm seasons over land masses such as Africa and South America. By analyzing long-term observation records, scientists can identify recurring months and regions of high sprite activity, providing insight into the connection between seasonal weather and upper atmosphere electrical phenomena. Positive lightning strikes are closely correlated with sprite occurrence. Unlike negative lightning, which is more common and usually strikes the ground from the lower part of the cloud, positive lightning originates in the upper region of the storm and carries a large quantity of charge. The resulting quasi-electrostatic field above the storm can trigger sprites. Observational campaigns have shown that nearly every observed sprite follows a strong positive lightning discharge. Lightning detection networks and high-speed cameras allow scientists to link the two events precisely in time and space. Positive lightning is more frequent in large, tall thunderstorms, particularly in regions with strong convection and deep cloud tops. Mapping the frequency and location of positive strikes provides a proxy for sprite likelihood and helps researchers identify hotspots of activity around the globe. Statistical analysis of sprite occurrence uses data from both ground-based and satellite observations. High-speed cameras and photometers record thousands of events over extended periods, allowing researchers to estimate frequencies, durations, and heights. Data show that most sprites appear in clusters above a single storm system, suggesting that regions of intense charge distribution within the cloud produce multiple events. Occurrence frequency varies widely by location and season, from rare events in some oceanic regions to dozens per night over the Great Plains during peak summer activity. Statistical models incorporate storm height, lightning intensity, and geographical factors to predict sprite likelihood. These models also account for observational bias, since sprites over oceans or in remote areas may go undetected without satellites. Patterns of global occurrence reveal that sprites are linked to large-scale atmospheric dynamics. Convective systems, such as mesoscale convective complexes, often produce multiple lightning events in a concentrated region. When conditions are favorable, clusters of sprites can appear above these storm systems. Researchers use both temporal and spatial analyses to identify correlations between sprite clusters and storm systems. Observations indicate that the largest and tallest storms tend to produce the most sprites, consistent with the physics of streamer formation in the mesosphere. By examining storm data, scientists can predict likely sprite events and target observation campaigns for maximum data collection. Mapping sprite occurrence globally also reveals connections with climate and regional weather patterns. Continental interiors with strong daytime heating and moisture convergence zones are prime locations. Regions influenced by monsoons or seasonal atmospheric instability show seasonal spikes in sprite activity. By comparing occurrence over decades, researchers can track whether changes in climate or storm patterns influence sprite frequency. While no long-term trends in global frequency have been definitively established, regional variations reflect the dependence on storm structure, altitude, and electrical charge distribution. This emphasizes that sprite occurrence is controlled by meteorological conditions rather than being random or constant across all storms. Observational networks combine multiple instruments to improve reliability of global measurements. Ground-based cameras, lightning detection systems, and satellite sensors work together to confirm sprite events. Stereo camera setups allow altitude measurement and structural analysis, while photometers provide data on brightness and energy. Satellite instruments, including optical and infrared sensors, detect transient luminous events over oceans and remote regions. By combining these datasets, researchers can build comprehensive maps of global occurrence, showing where sprites are most frequent and under what conditions. These maps are essential for understanding the relationship between sprites, thunderstorms, and the electrical dynamics of the upper atmosphere. Statistical modeling also incorporates seasonal variability and lightning characteristics. Data indicate that sprites are more likely in storms with positive lightning that occurs above 35 kilometers in cloud tops. The probability increases with storm height, duration, and electrical intensity. By quantifying these factors, researchers can calculate occurrence frequency for different regions and times of year. Models confirm observational findings. Continental interiors with tall thunderstorms produce the highest sprite activity, while oceanic storms and low-altitude clouds are less likely to generate these phenomena. The combination of modeling and direct observation provides a predictive framework for sprite research, allowing scientists to anticipate where and when these events are most likely to occur. In addition to location and season, sprite morphology also varies with storm characteristics. Taller storms with widespread charge separation tend to produce large, carrot-shaped sprites with multiple tendrils. Shorter storms, or those with uneven charge distribution, may produce smaller, column-like sprites. Observers have catalogued these variations to understand the influence of underlying storm structure on sprite form. The global distribution of shapes and sizes provides additional insight into how atmospheric and electrical conditions interact. Each observation contributes to a larger picture of the global patterns, reinforcing the connection between storm intensity, lightning type, and sprite development. Overall, the global study of red sprites shows that these phenomena are closely tied to thunderstorms, positive lightning, and the structure of the atmosphere. They are most common over continental interiors during peak storm seasons, but they can occur worldwide under favorable conditions. Clustering patterns, altitude ranges, and sprite morphology are all influenced by storm characteristics. Statistical analysis, modeling, and satellite observations confirm these trends, providing a detailed understanding of where and when sprites are likely to appear. By studying these global patterns, scientists gain insight not only into sprite behavior, but also into the broader electrical and meteorological processes that shape the upper atmosphere above storms. Through careful measurement, observation, and modeling, the once elusive red sprite is now recognized as a consistent and measurable feature of Earth's atmosphere, connecting storms on the ground with luminous displays high above. Red sprites are more than just luminous displays. They interact directly with the upper layers of the atmosphere. When a sprite forms, electrons accelerated by the quasi-electrostatic field collide with molecules of nitrogen and oxygen. These collisions excite the molecules, sometimes breaking chemical bonds or forming ions. The resulting ionization alters the local electrical environment, creating transient currents that briefly flow through the mesosphere. Although these currents are small compared to the power of the storm below, they are significant at high altitudes, where the air is thin and electrical conduction is limited. The ionized channels created by sprites can persist for fractions of a second, influencing how electric fields evolve above the storm. By mapping these currents and ionization patterns, scientists gain insight into the behavior of the upper atmosphere and how energy is transferred from thunderstorms to higher layers. The chemistry of the mesosphere is affected in subtle ways by sprite activity. When nitrogen molecules are excited, they can produce reactive species such as nitric oxide and other transient compounds. These molecules interact with the surrounding air, temporarily modifying chemical composition and energy distribution. Although each sprite contributes only a small change, the cumulative effect over many events can influence mesospheric chemistry in localized regions. Temperature in these layers may be slightly affected as energy from the electrical discharge heats the surrounding gases. Measuring these effects requires sensitive instruments aboard balloons, rockets, or satellites, capable of detecting small changes in composition and temperature at altitudes of 50 to 90 kilometers. Understanding these interactions is important for atmospheric modeling, as it shows how storms influence layers far above their clouds. Sprites also play a role in electromagnetic propagation. The sudden ionization of a channel creates a temporary path for electrical signals. These transient currents can interact with naturally occurring electromagnetic waves, such as Schumann resonances or radio waves traveling through the ionosphere. By briefly altering the conductivity of the mesosphere, sprites can affect how these waves propagate. Scientists study these interactions to learn more about the electrical properties of the atmosphere and how disturbances from storms can influence communication signals and natural electromagnetic phenomena. Measurements show that sprite-induced currents are short-lived, lasting only milliseconds, but they demonstrate that storms are connected electrically to higher atmospheric layers in ways that extend beyond visible light. Cosmic rays and other high-energy particles also interact with sprite events. The mesosphere is constantly bombarded by charged particles from space. These particles provide free electrons that can influence streamer initiation and growth. When a sprite occurs, the presence of cosmic ray-induced electrons can help seed the development of streamers, allowing them to propagate upward more efficiently. Similarly, the sprite itself temporarily increases ionization, affecting how cosmic rays and other high-altitude particles interact with the atmosphere. These complex interactions between natural radiation, storm-induced electrical fields, and transient luminous events illustrate that the upper atmosphere is a dynamic environment where multiple forces converge and produce observable phenomena. Sprites can occur alongside other high-altitude displays, such as auroras. In polar regions, auroras dominate the night sky, but occasional thunderstorms can produce sprites at lower latitudes. While auroras are caused primarily by charged particles from the solar wind interacting with the ionosphere, sprites result from lightning-generated fields. Both phenomena involve excitation of atmospheric molecules and emission of light, but the mechanisms differ. Studying sprites alongside auroras helps scientists understand how different energy sources affect the upper atmosphere. It also highlights that electrical phenomena are not confined to the troposphere. Energy from storms can propagate upward, interacting with other natural processes and revealing connections between weather, climate, and space environment. The transient currents generated by sprites contribute to a small but measurable effect on the electrical balance of the atmosphere. Each sprite forms ionized channels that conduct charge briefly, redistributing electrons in the mesosphere. These currents are too weak to influence the storm below significantly, but they demonstrate that energy from thunderstorms extends well above the cloud tops. In some cases, measurements suggest that sprite activity can slightly alter the local electric potential, which could influence subsequent lightning or upper atmosphere events. Observations and models continue to explore how repeated sprite activity over a storm system might modify mesospheric electrical conditions over time, providing insight into the coupling between tropospheric and mesospheric electricity. Scientists use laboratory simulations to better understand these interactions. Low-pressure chambers allow researchers to reproduce mesospheric conditions, creating streamer discharges in nitrogen-rich air at low density. By observing how these artificial sprites form and decay, researchers measure ionization levels, energy deposition, and molecular reactions. Laboratory studies complement field observations, confirming that sprites alter the chemical and electrical environment of the mesosphere in measurable ways. The combination of in situ measurements, high-speed imaging, and lab experiments provides a comprehensive picture of how sprites interact with their surroundings, showing that these brief flashes of light are part of a larger dynamic system. Sprites also offer insight into climate modeling. By temporarily changing the ionization and chemistry of the mesosphere, sprites influence the propagation of energy and chemical compounds at high altitudes. While each individual event has a minor effect, the aggregate influence of many sprite occurrences worldwide could be relevant for mesospheric dynamics over time. Climate models that include upper atmosphere chemistry and electrical effects must consider transient luminous events like sprites to accurately represent energy transfer and chemical interactions. This understanding helps improve simulations of atmospheric circulation, energy balance, and the behavior of charged particles in the mesosphere and lower ionosphere. Interactions with other upper atmosphere phenomena, such as elves and blue jets, further illustrate the complexity of mesospheric electricity. Elves, expanding disc-shaped flashes caused by electromagnetic pulses, temporarily increase ionization over hundreds of kilometers, while blue jets transport energy from cloud tops into the stratosphere. Sprites, by forming streamer channels, concentrate energy vertically in columns, creating localized regions of ionization and excitation. Together, these phenomena demonstrate that thunderstorms generate a spectrum of electrical events, each with distinct physical mechanisms and effects on the atmosphere. Studying sprites in this context helps scientists understand how energy and charge move vertically through the atmosphere, from the turbulent storm layers to the mesosphere and beyond. Even subtle temperature changes can result from Sprite activity. As electrons collide with molecules, they transfer energy, producing brief heating along the streamer channels. While the overall effect on mesospheric temperature is small, localized heating influences the behavior of surrounding air, potentially affecting the propagation of subsequent electrical discharges. Observations indicate that repeated Sprite events over the same storm or region may create small, cumulative effects, altering the local conditions for future high-altitude electrical phenomena. Understanding these effects is essential for modeling the upper atmosphere and for predicting how thunderstorms influence layers far above the clouds. Sprites also provide natural laboratories for studying the electrical conductivity of the mesosphere. Measuring the propagation of currents, the response of molecules, and the decay of ionization allows scientists to estimate the resistance and capacitance of these high-altitude layers. These measurements are critical for understanding how energy from storms is transmitted upward and how it interacts with electromagnetic waves. They also inform studies of the global electric circuit, which links the surface, thunderstorms, ionosphere, and magnetosphere. By observing sprites and quantifying their effects, researchers gain a direct view of how localized electrical events connect to the larger system of atmospheric electricity. The implications of Sprite activity for space weather and planetary science are also significant. By altering the ionization and electrical properties of the mesosphere, Sprites may influence how charged particles from the solar wind interact with Earth's upper atmosphere. Understanding these interactions helps scientists predict changes in ionospheric conductivity, radio wave propagation, and the behavior of natural electromagnetic fields. In addition, Sprites provide analogues for studying high-altitude electrical phenomena on other planets, such as lightning-induced emissions in the upper atmospheres of Jupiter and Saturn. Research on Earth offers a baseline for interpreting observations of extraterrestrial storms and upper atmosphere discharges. Through observation, modeling, and laboratory experiments, scientists have confirmed that sprites are not merely visual curiosities. They actively shape the electrical, chemical, and thermal environment of the mesosphere. By creating ionized channels, modifying local chemistry, generating transient currents, and interacting with cosmic rays and auroras, sprites influence multiple layers of the atmosphere. The study of these interactions provides insight into energy transfer from thunderstorms to higher altitudes, contributing to a more complete understanding of atmospheric dynamics. Sprites reveal that the upper atmosphere is not passive, but responds to electrical activity below, and that storms produce effects that reach far beyond their visible clouds. Finally, the study of sprite interactions emphasizes the interconnectedness of atmospheric systems. A storm on the ground sends energy upward, producing light, currents, and chemical changes tens of kilometers above the clouds. The mesosphere responds to each event, and cumulative effects over time help shape the behavior of high-altitude layers. By integrating these observations into broader atmospheric models, scientists gain a richer understanding of the global electric circuit, energy transfer, and the coupling between weather and space phenomena. Sprites thus serve as windows into processes that are otherwise invisible, illustrating how localized events can influence the larger system of Earth's atmosphere and informing both climate science and space weather research. Red sprites are not only a subject of scientific curiosity, they have practical relevance for modern technology. Aircraft flying at high altitudes can pass through regions where the upper atmosphere is temporarily ionized by sprites. Although the energy of individual sprites is too low to damage airplanes directly, the sudden electrical currents and localized ionization can affect onboard sensors or instruments that rely on electromagnetic signals. Pilots and aviation engineers have studied sprite-prone regions to understand how thunderstorms extend their influence upward, beyond cloud tops, and how this might interact with high-altitude flight. Satellite instruments, flying hundreds of kilometers above the Earth, are also affected by transient luminous events. Electrical discharges in the mesosphere temporarily alter the ionospheric conductivity, influencing radio wave propagation and signal clarity. By understanding the frequency, timing, and distribution of sprites, engineers can anticipate minor disruptions and improve system resilience. Communication systems are particularly sensitive to high-altitude electrical phenomena. Radio waves, both very low frequency, VLF, and higher bands, rely on ionospheric conditions for propagation. When a sprite occurs, it briefly changes the ionization of the mesosphere, which can alter the reflection and transmission of radio waves. These effects are small but measurable, and they provide natural experiments for studying electromagnetic wave behavior in variable atmospheric conditions. By observing sprite-induced changes in radio signal propagation, scientists can refine models of the upper atmosphere's electrical properties. These insights have practical applications, including improving long-range communication reliability and understanding how storms influence global electromagnetic systems. Modern monitoring of red sprites has advanced significantly with the integration of satellites, radar, and artificial intelligence. Space-based instruments provide a broad view of storm systems and can detect transient luminous events in remote or otherwise unobservable regions. Satellites equipped with optical sensors capture the red flashes across large geographic areas, while complementary radar systems track the underlying storm dynamics. High-speed cameras on the ground provide detailed structural and temporal data. The combination of these tools allows researchers to link sprite events to storm characteristics, lightning types, and atmospheric conditions. Artificial intelligence algorithms assist in processing the vast amounts of visual and sensor data, identifying sprites within thousands of images or hours of video, and distinguishing them from other phenomena such as lightning reflections or camera artifacts. Machine learning models can classify sprite shapes, brightness, and branching patterns, accelerating the analysis of complex datasets. AI-assisted monitoring also improves predictive modeling of sprite occurrence. By analyzing historical storm and sprite data, machine learning systems can identify patterns that precede sprite formation. Variables such as storm height, lightning polarity, atmospheric pressure, and humidity can be combined to estimate the probability of a sprite occurring above a given storm system. These predictive models enhance observation campaigns, allowing scientists to focus high-speed cameras or satellite sensors on storms with the greatest likelihood of producing sprites. In this way, AI not only increases efficiency, but also expands understanding of how sprite formation is linked to storm dynamics and upper atmosphere electrical conditions. The integration of satellite data and ground-based monitoring provides a near real-time view of global sprite activity. Networks of cameras and sensors, combined with lightning detection systems, track storm, evolution, and sprite occurrence simultaneously. Observers can now measure the time between a strong positive lightning strike and the resulting sprite with millisecond precision, revealing consistent correlations across storms worldwide. This continuous monitoring allows scientists to quantify sprite frequency, spatial distribution, and vertical development on a global scale. Satellite data also confirm that sprites are not limited to certain regions. They occur wherever conditions produce strong positive lightning and tall storm clouds, illustrating the universality of the phenomenon. Sprites also contribute to studies of atmospheric electricity and the global electric circuit. By creating temporary ionized channels and transient currents, they form part of a larger system that connects the surface, thunderstorms, and ionosphere. Monitoring these events improves understanding of how energy is transferred vertically through the atmosphere. Electrical measurements during Sprite events reveal patterns in charge redistribution and how the atmosphere responds to intense electrical activity below. This knowledge is valuable for space weather research, as it links the behavior of terrestrial storms to conditions in the upper atmosphere and near Earth space. In addition to direct observation, computational models simulate how sprites interact with storm-generated electric fields. High-resolution simulations incorporate storm size, lightning intensity, altitude, and atmospheric composition to predict the shape, height, and brightness of sprites. These models are calibrated against satellite and ground-based observations, improving accuracy over time. By comparing simulated events to actual measurements, researchers refine the understanding of how lightning and atmospheric conditions produce these transient luminous phenomena. Advanced simulations also explore the effects on radio wave propagation, ionospheric conductivity, and mesospheric chemistry, bridging observational science with practical technological concerns. Radar and LiDAR instruments complement optical observations by providing data on storm structure and cloud top height. Knowing the vertical extent of the thunderstorm allows researchers to estimate the energy of the lightning strikes that trigger sprites. Taller storms with stronger updrafts tend to produce more intense sprites, and radar data help identify these target storms. LiDAR can detect fine-scale features in the atmosphere, such as aerosol density and cloud microstructure, which influence how electrical fields propagate upward. This integrated approach ensures that sprite observation is not only visual, but also tied to measurable atmospheric parameters. Real-time sprite monitoring also benefits aviation and satellite operations. Airlines can adjust flight paths to minimize exposure to strong electric fields above storms, and satellite operators can account for potential transient ionospheric changes that may affect signal clarity. Ground-based VLF and HF radio networks use sprite data to refine signal propagation models, predicting minor disruptions caused by mesospheric ionization. By understanding the timing, location, and intensity of sprites, engineers and scientists can incorporate these phenomena into operational planning, reducing the potential impact on sensitive systems. The ongoing development of AI algorithms has transformed sprite research from reactive observation to proactive prediction. Large datasets of lightning strikes, storm measurements, and historical sprite events train models to forecast likely sprite activity. Researchers can now anticipate which storms are most likely to produce sprites, optimizing the deployment of high-speed cameras and satellites. These predictive capabilities improve both data collection and understanding of storm electrical interactions. In addition, predictive models support broader atmospheric studies by linking mesospheric phenomena to storm evolution, lightning patterns, and upper atmosphere electrical conditions. Modern monitoring also allows long-term studies of sprite occurrence trends. By maintaining networks of cameras and satellites over decades, scientists track variations in sprite frequency, morphology, and global distribution. These trends can be compared with changes in storm patterns, climate variability, and atmospheric composition. Long-term observation reveals how large-scale weather and climate patterns influence Sprite activity, providing insights into the broader electrical and meteorological systems of the planet. Continuous data collection ensures that Sprites are no longer isolated curiosities, but integral components of atmospheric science and technological planning. The use of multiple monitoring tools simultaneously, satellites, radar, cameras, AI, and lightning networks, provides a complete picture of Sprite dynamics. Each tool contributes unique information. Satellites observe global distribution, cameras capture fine structural detail, radar tracks storm tops, and AI processes large datasets efficiently. Together, these technologies allow real-time monitoring, detailed study, and predictive modeling. Scientists can measure the altitude, duration, and branching of each Sprite, while understanding the storm context that produces it. This integrated approach demonstrates how modern technology extends human perception, revealing phenomena that were invisible just decades ago. Sprites also provide opportunities for testing atmospheric and space models. By observing how they alter ionospheric conditions and electrical currents, scientists evaluate the accuracy of simulations predicting the behavior of charged particles and electromagnetic waves. These tests are critical for satellite communication, radio navigation, and forecasting space weather events. Sprites act as natural laboratories for studying how electrical energy from thunderstorms propagates upward, interacts with the mesosphere, and affects high-altitude systems. Observations collected with modern tools improve models that are essential for both scientific research and practical applications. In conclusion, red Sprites play a role in modern technology and monitoring. They influence high-altitude conditions relevant to aviation, satellites, and radio communication. Observing these phenomena improves understanding of electrical processes, transient currents, and ionization in the mesosphere. Modern monitoring integrates satellites, radar, high-speed cameras, and AI to track Sprites globally and predict their occurrence. This combination of technology allows scientists to study Sprite dynamics in real time, model their effects, and apply the knowledge to practical systems. By bridging observation, simulation, and technology, red Sprites have become more than natural curiosities. They are integral to understanding and managing high-altitude electrical activity on Earth. Red Sprites have captured the public imagination as much as they have intrigued scientists. Their sudden, delicate flashes high above thunderstorms present a visual spectacle that is both rare and striking. For decades, only pilots or researchers flying above storms had the chance to witness them firsthand. But as photographic and video evidence became widely available, Sprites began appearing in documentaries, educational programs, and popular media. Television specials focused on atmospheric phenomena often feature high-speed footage of red columns stretching upward, giving viewers the sense of seeing a previously hidden layer of the sky. Online platforms and science channels have further amplified this exposure, allowing people around the world to view Sprites in motion, often accompanied by explanations of the physical processes behind the fleeting flashes. These visual representations highlight the connection between thunderstorms and the upper atmosphere, making complex science accessible to the public. Artists and filmmakers have drawn inspiration from the mysterious red flashes. The unique shape of Sprites, with their branching tendrils and glowing vertical columns, lends itself to visual storytelling. Filmmakers working on documentaries or science fiction have incorporated Sprite imagery to evoke wonder and the unseen activity in the sky. Illustrators and digital artists recreate Sprite forms to capture the beauty of upper atmosphere lightning, often using simple color palettes of red, purple, and orange to represent the natural light emitted by excited nitrogen molecules. By translating sprite phenomena into visual art, creators help the public connect emotionally to a phenomenon that is otherwise invisible without special equipment. The artistic representation of sprites reinforces the idea that science and visual experience can coexist, making intangible phenomena more tangible to observers. Writers and educators often use sprites as examples to convey scientific concepts in a compelling way. Textbooks, popular science books, and online articles describe the physics of sprite formation, their connection to lightning, and the electrical coupling of atmospheric layers. Using sprite imagery, authors illustrate how energy moves from thunderstorms to the mesosphere, making abstract concepts concrete. By linking visual spectacle to scientific explanation, writers bridge the gap between awe and understanding. Readers are not only captivated by the beauty of the phenomena, but also gain insight into the electrical and chemical processes that produce it. In classrooms, sprite images are used to discuss topics such as atmospheric electricity, ionization, and the global electric circuit, bringing high-altitude physics into a context that is easy to grasp. Public engagement has also contributed directly to sprite research. Citizen scientists, storm chasers, and amateur photographers often capture sprite events with sensitive cameras and share their findings with professional researchers. Many sprite studies include contributions from volunteers who operate high-speed cameras or coordinate observations during summer thunderstorms. By increasing the number of observation sites, citizen science expands the geographic coverage of sprite monitoring, allowing for detection in regions that may not be accessible to professional teams. These contributions enrich the scientific dataset, providing additional temporal and spatial information that helps researchers understand sprite frequency, morphology, and behavior. Collaboration between professionals and the public demonstrates that sprite research is not limited to laboratory or institutional work, but is enriched by broader participation. Science communication surrounding sprites emphasizes both the wonder and the understanding of natural processes. Researchers often present sprites as examples of how extreme weather connects to higher layers of the atmosphere, illustrating that thunderstorms do more than produce rain and lightning. They influence the mesosphere and ionosphere as well. Documentaries and educational programs use slow motion and high-speed footage to reveal details that the naked eye cannot see, showing how streamers grow, branch, and fade. Narration guides viewers through the sequence of events, linking visible flashes to the underlying physical mechanisms. By combining observation with explanation, science communicators make sprites approachable, showing that these elusive flashes are both beautiful and scientifically meaningful. The visual appeal of sprites has also encouraged interdisciplinary collaboration. Scientists working with filmmakers, illustrators, and educators develop accurate visualizations that reflect the physical properties of sprite events. High-speed photography and spectral analysis provide the basis for animation and computer-generated imagery, ensuring that depictions of sprites remain faithful to their natural appearance. This collaboration strengthens public understanding, as viewers see phenomena that are scientifically grounded while still visually captivating. It also reinforces the value of observational data, demonstrating that accurate science enhances rather than diminishes artistic and narrative expression. Cultural references to sprites occasionally appear in music, literature, and poetry. Their sudden ethereal flashes inspire metaphorical language, often symbolizing unseen forces, fleeting moments, or the hidden beauty of nature. Authors and poets may describe a stormy sky as alive with red sparks, or refer to sprites when evoking mystery or revelation. These references, while not scientific, contribute to the popular imagination and underscore the human fascination with phenomena that occur at the edge of perception. Through these cultural touchpoints, sprites enter everyday consciousness, highlighting how natural events can influence creativity and storytelling. Educational outreach programs frequently include sprite phenomena in curriculum modules on weather, electricity, or atmospheric science. By showing students real video footage of sprites and explaining the connection to thunderstorms and upper atmosphere physics, educators provide a memorable experience that combines visual learning with conceptual understanding. Experiments and simulations in classrooms may replicate the conditions that produce streamer discharges, using small-scale laboratory setups or interactive software to model ionization and light emission. Such experiences reinforce learning, making high-altitude electrical phenomena tangible without leaving the ground. Students gain insight into both the science and the observational techniques that allow researchers to study these elusive flashes. Citizen science platforms often organize coordinated Sprite observation nights, especially during seasons of high thunderstorm activity. Volunteers set up cameras and synchronize their observations using online networks, allowing for real-time reporting and subsequent data analysis. The contributions of these citizen scientists extend the reach of research beyond what professional teams could achieve alone, providing dense temporal coverage across multiple regions. The resulting datasets allow for the study of sprite morphology, frequency, and correlation with positive lightning strikes. Public participation also promotes broader awareness of atmospheric science, as observers become personally invested in understanding the natural world. By actively contributing to scientific research, individuals connect curiosity with data collection, enhancing both engagement and knowledge. Media coverage of sprites often emphasizes their fleeting and elusive nature. Documentaries highlight that sprites last only a few milliseconds and appear above storms that might be hundreds of kilometers away. This rarity adds to their fascination, making each observation noteworthy. Slow-motion footage, combined with explanatory narration, helps viewers understand the physical processes occurring in the atmosphere. By focusing on the measurable, predictable aspects of sprite formation, media presentations balance awe with factual understanding. Audiences learn that what seems magical is governed by electrical fields, ionization, and atmospheric chemistry, demonstrating that science can explain the extraordinary while preserving wonder. Sprites also play a role in bridging science with public curiosity about space and extreme weather. Observers often draw parallels between sprites and other atmospheric or planetary phenomena, such as auroras or lightning on Jupiter. Documentaries contextualize sprites within the broader framework of atmospheric science, showing that energy and electrical activity extend well above the clouds and into regions of low air density. By linking observable events to larger scientific principles, communicators demonstrate the relevance of sprites to understanding Earth's atmosphere as a dynamic, interconnected system. This perspective encourages viewers to see thunderstorms not just as local weather events, but as part of a global network of electrical and chemical interactions. Overall, public fascination with red sprites reflects a combination of aesthetic appreciation, cultural interpretation, and scientific curiosity. The media, education, and citizen science initiatives have expanded awareness of these elusive flashes, while accurate representation ensures that wonder is grounded in factual understanding. Artists, filmmakers, writers, and scientists all contribute to the ongoing dialogue about sprites, making them accessible to broad audiences. By combining observation, explanation, and creative interpretation, the phenomenon of red sprites connects human imagination with atmospheric reality, allowing the public to engage with a scientific process that was once hidden above storm clouds. In doing so, science, communication bridges awe and understanding, demonstrating that even the most fleeting natural events can inspire both wonder and insight into the workings of the upper atmosphere. The study of red sprites continues to expand as technology and observation methods improve. Researchers are now able to detect these fleeting flashes more consistently, mapping their occurrence across the globe and linking them with the underlying storm systems. The integration of satellites, high-speed cameras, radar, and artificial intelligence allows for unprecedented detail, providing both spatial and temporal precision. Scientists can measure the height, duration, shape, and brightness of sprites, while correlating them with lightning type, storm intensity, and atmospheric conditions. These capabilities make it possible to study sprite formation systematically, rather than relying on chance observations. By understanding the patterns and mechanisms behind sprite events, researchers gain deeper insight into the electrical coupling between the troposphere, mesosphere, and ionosphere. Looking forward, scientists are focusing on the implications of sprites for atmospheric science. Each sprite event represents a small, temporary transfer of energy from thunderstorms into higher layers of the atmosphere. By studying these events in detail, researchers can understand how electrical energy from storms influences ionization, chemical reactions, and transient currents in the mesosphere. Insights from sprites contribute to models of the global electric circuit, providing information about how the Earth's atmosphere maintains its electrical balance. These findings also inform climate models, as the interactions between thunderstorms and the upper atmosphere influence energy distribution, chemical composition, and the behavior of charged particles at high altitudes. As more data are collected, scientists refine predictions about how electrical and chemical processes are interconnected across layers of the atmosphere. The development of predictive models is another area of focus. Using historical observations of storm behavior and sprite occurrence, combined with real-time lightning data, researchers are creating systems that estimate the likelihood of sprites above specific storms. Machine learning algorithms process vast datasets of lightning polarity, cloud height, storm intensity, and geographic location to identify conditions most likely to produce sprites. These models improve observation efficiency by guiding high-speed cameras and satellites toward active storms, ensuring that transient luminous events are captured for analysis. Over time, predictive capabilities may also allow scientists to anticipate the electrical impact of thunderstorms on the upper atmosphere, including effects on communication systems and the global electric circuit. Sprites also continue to serve as natural laboratories for studying high-altitude electrical phenomena. Laboratory experiments replicate mesospheric conditions using low-pressure chambers and gas mixtures similar to Earth's atmosphere at 50 to 90 kilometers altitude. Streamer discharges in these chambers help researchers measure ionization, energy transfer, and molecular excitation. By comparing laboratory results with field observations, scientists can validate models of sprite formation and behavior. This combination of observation, experimentation, and modeling strengthens understanding of the physics involved, revealing how small-scale processes influence the broader dynamics of atmospheric electricity. Laboratory studies also enable exploration of extreme conditions that cannot be directly observed in nature, expanding the range of possible scenarios and outcomes. The implications for technology remain significant. Aircraft and satellite operations benefit from improved understanding of Sprite activity. Pilots can be informed about regions with higher probabilities of upper atmosphere, electrical events, while satellite engineers can account for potential temporary disruptions in ionospheric conditions. Research into Sprite effects on radio wave propagation enhances models used by communication networks, improving prediction and mitigation strategies. As our technological reliance on satellites, navigation systems, and high-frequency communication grows, knowledge about high-altitude electrical phenomena becomes increasingly important. Sprites, once considered curiosities, are now recognized as relevant to practical applications in aviation, space operations, and electromagnetic systems. Citizen science continues to play a role in advancing Sprite research. Enthusiasts, storm chasers, and photographers contribute observations and imagery from locations around the world. Coordinated observation campaigns during peak storm seasons allow citizen scientists to supplement professional datasets, extending the coverage of Sprite detection and enabling comparative studies across continents and oceans. Public participation also promotes interest in atmospheric science, inspiring students, educators, and amateur observers to engage with the natural world. Through careful reporting and collaboration, citizen-collected data become part of the larger scientific effort, demonstrating the value of widespread observation and fostering a connection between research and public curiosity. Future research also emphasizes the interactions of sprites with other high-altitude phenomena. Studies are ongoing to understand how sprites influence or are influenced by elves, blue jets, auroras, and cosmic rays. These events occur in overlapping regions of the upper atmosphere and can interact in subtle ways. By studying these interactions, scientists gain a more complete understanding of mesospheric and ionospheric dynamics. Observations and simulations reveal how energy from thunderstorms propagates upward, how ionization channels form, and how transient electrical currents influence both natural and technological systems. The combination of these phenomena illustrates the complexity of Earth's atmosphere, showing that sprites are part of a broader network of high-altitude electrical events. Global monitoring networks are expanding to capture long-term trends in Sprite activity. Satellite programs, lightning detection networks, and coordinated ground-based observations provide data over decades, allowing researchers to track variations in occurrence frequency, morphology, and geographic distribution. By analyzing these trends, scientists can assess the influence of climate variability, storm intensity, and atmospheric composition on sprite formation. Such studies inform broader questions about the electrical and chemical processes of the upper atmosphere, demonstrating how localized storm activity can have effects that extend to tens of kilometers above the clouds. Long-term observation is crucial for integrating sprite phenomena into comprehensive models of atmospheric behavior and global electrical balance. Education and science communication remain vital for ensuring that knowledge of sprites continues to reach a wide audience. Documentaries, high-speed imagery, classroom activities, and citizen science programs make the phenomena accessible to non-specialists. By combining visual appeal with accurate scientific explanation, educators and communicators inspire curiosity while reinforcing factual understanding. The public becomes aware that sprites are not only beautiful flashes, but also measurable events that reveal the workings of the atmosphere. This approach builds appreciation for natural phenomena supports scientific literacy, and encourages ongoing engagement with research and observation. Looking ahead, the study of red sprites exemplifies the intersection of observation, theory, and technology. From their first elusive sightings to the sophisticated monitoring networks of today, these transient, luminous events reveal the dynamic relationship between thunderstorms and the upper atmosphere. Each new observation enhances understanding of electrical coupling, ionization, and chemical interactions in high-altitude regions. Integration of AI, satellite data, high-speed cameras, and citizen observations continues to push the boundaries of what is possible, turning a rare atmospheric curiosity into a well-characterized scientific phenomenon. Researchers can now analyze sprite formation with precision, predict likely occurrences, and explore their influence on technology, weather, and atmospheric chemistry. Ultimately, red sprites illustrate the richness and complexity of Earth's atmosphere. They show how storms can influence layers far above their clouds, transmitting energy and generating chemical and electrical effects that are measurable yet fleeting. By studying these phenomena, scientists gain insight into the subtle processes that maintain the global electric circuit and shape mesospheric conditions. Sprites demonstrate that even short-lived rare events contribute to the broader understanding of atmospheric dynamics. As research continues, they will remain both objects of scientific inquiry and sources of wonder, bridging human curiosity with measurable physical processes. The combination of observation, experimentation, modeling, and public engagement ensures that red sprites remain a central focus in the study of Earth's high-altitude electrical environment, linking storms, the mesosphere, and ionosphere in a continuous, observable system.